Bismillahirrahmanirrahim. Our next topic is signal flow graph. Signal flow graph is actually another method to model the system. You have already discussed some modeling methods. You have represented your system through differential equations. You have represented your system through block diagrams, and now this is another method. You will represent your system using signal flow graph. This is actually the method of modeling of a system, and you may find the relationship between control variable and input variable using the signal flow graph. Bismillahirrahmanirrahim. Our next topic is signal flow graph. This is actually a pictorial representation of the system, another way of modeling the system. You have already discussed some modeling methods, how we represent our systems. You have already represented your systems by block diagram. You have already represented your systems through differential equations. By these methods, we are actually driving the relationship between our control variable and input variable. So this is more convenient method as compared to the block diagram, and we will find the transfer function using some rules. While we apply some rules on the signal flow graph, we will find the transfer function, we will find the relationship between the control variable and the output on the input variable. Okay, now this is another lecture of the signal flow graph. We have already covered some topic. Now we see some other things. Okay, now we continue the topic of the signal flow graph. Now we have already covered many topics, and we'll see some more things in details now for the signal flow graph. What will be covered in this topic? First we'll cover some basic definitions with examples. What are the basic definitions? What are the things involved while constructing the signal flow graph, like branches and forward path and backward path, and then we'll construct our signal flow graph. We'll see how we'll construct by using the equations of the systems. How can we construct the signal flow graph? Then we will use Mason's gain formula to find the transfer function of the system, and then we'll see some examples, and then we'll see how can we convert our block diagram to signal flow graph. Block diagram is actually sometimes cumbersome to solve and difficult, and sometimes but all the times we have to redraw it again and again to reduce it into the canonical form to find the transfer function. So it is easier if we first convert our block diagram to signal flow graph, and then we find the transfer function using the Mason's rule. So first we'll see the construction and definitions, and then we'll find the transfer function using Mason's rules, and then we'll convert our block diagram into signal flow graph to find the transfer function. We have already covered some basic definitions, how we'll construct the signal flow graph. We have explained in details the Mason's gain formula, and we have seen examples in detail how we apply this Mason's gain formula to the signal flow graph we have constructed. I think I have already discussed that one example always I will do in detail whenever I take physical in the classroom, and just right now in online classes I have explained in detail one example. Now we'll see some more examples, some more things which comes under signal flow graph, how we can apply the Mason's rule for different conditions. And then we'll see the conversion of block diagram to signal flow graph, which is an easier method as compared to block diagram. We'll see some rules how we'll convert our block diagrams to signal flow graph, and then after conversion we'll apply the same Mason's gain formula to find the control ratio or the transfer function from the signal flow graph. Obviously the transfer function obtained from the block diagram and that obtained from the signal flow graph, both will be same. So this is an alternate method to find the signal flow graph, that we convert our block diagrams into the signal flow graph. Okay, now we'll see some other example. This is example. In these examples, you are watching that we have 7 nodes: y1, y2, y3, y4, y5, y6 and y7. And the question is, find y2 upon y1, y4 upon y1, y6 upon y1, y7 upon y1 using Mason's rule. So I think you have observed here that y7 upon y1 is the overall transfer function, that is output upon input, and the rest are not direct output upon input or some intermediate nodes like y6 upon y1 is not the output node. Here the output node not y6, rather it is y7, and here y2 upon y1, in this y1 is input node but y2 is a non-input node, sorry, non-output node. Similarly y4 upon y1, y4 upon y1, y1 is input node but y4 is not an output node. So we can see that we can apply this gain formula in different conditions like we see in this example. Okay, for any transfer function we want to find either it is y2 upon y1 or y6 upon y1 or y7 upon y1. First of all we have to find y7 upon y1. So we'll work on it first to find y7 upon y1. Either we are going to find y2 upon y1 or y7 upon y1 or y6 upon y1. First we work for y7 upon y1. So we'll first find out y7 upon y1, then we'll find the remaining terms. I hope all of you have remembered that when we apply the Mason's rule, first we have to count the number of forward paths so that we can set the formula to find the transfer function. So here in this example, when we count the number of forward paths, you can see this carefully and you will see that we have two forward paths here. The first forward path is the straight line in which the branch gains are G1, G2, G3 and G4. And the branch gain from y1 to y2 is 1 and y6 to y7 is also 1. So the overall forward path gain is the product of the branch gains, that is G1, G2, G3, G4, and another forward path is from y1 to y2, then y2 to y3, then y3 to y6 and then y7. So along this path you have two branches, G1 with branch gain G1 and G5, and another two branches, rest of the two branches have gained 1. So the product of all these branch gains will be G1, G5. So here we have two forward paths. There is no other forward path. The definition of the forward path, I hope you have remembered that from input to output, such that no node should be traversed more than once. So we have two forward paths, P1, P2. That is P1 is G1, G2, G3, G4 straight line, and P2 is G1, G5. And please note that first we are calculating the overall output upon input node gain. We are first calculating y7 upon y1. y7 is the output node, y1 is the input node. So first of all we calculate y7 upon y1 and then we see the remaining terms, that is y2 upon y1 or y4 upon y1 and so on. After carefully counting the number of forward paths, next we'll have to set our formula. As we have two forward paths, the formula will become P1 del 1 plus P2 del 2 upon del. In some books, forward paths are actually represented by M1, so we can write it as M1 del 1 plus M2 del 2 upon del. So because of two forward paths, we have set the formula as P1 del 1 plus P2 del 2 upon del. Now on the formula of P1 del 1 plus P2 del 2 upon del, we have already calculated P1, P2, which is the forward path. Now we have to calculate del, and to calculate del, first we have to see how many loops are present. So in this diagram you can see that we have 4 single loops. The first one is P11, that is minus G3H2. I have taken this as first loop. P21 is minus G1H1. This is the second loop. The third loop is the bigger one, which is actually G1, G2, G3 and H3, minus sign with H3. And the fourth loop is H4, which is minus H4, which is a self loop. So here we have 4 single loops. After counting the number of single loops, now we'll see the combination of 2 non-touching loops and the 3 non-touching loops. So first we see that L1 and L2, single loop 1 and single loop 2 are non-touching because there is no node common between the two loops. So we can write P12 as minus G1H1 multiplied by minus G3H2. I hope you have remembered that the product of the branch gains for all two loops will be the total gain. So P12 is the combination of two non-touching loops. The first combination P12 is minus G1H1 and minus G3H2. The second combination is second loop, that is minus G1H1 multiplied by the fourth one, that is minus H4. Again, there is no node common, so this is the second combination of the two non-touching loops. The third combination is the first and the fourth loop, that is minus G3H2 and minus H4. Again, there is no node common. And the fourth combination is the third and fourth loop, which we have counted earlier. So this is minus G1, G2, G3, H3 and minus H4. So we have four combinations or two non-touching loops, and there is one combination of three non-touching loops, which is loop 1, loop 2 and loop 4. That is the product of the loop gains of these three loops. P13 is G1H minus G1H1 multiplied by minus G3H2 multiplied by minus H4. So we have four combination of two non-touching loops and one combination of three non-touching loops. Now we calculate the value of del. The formula of del, if you have remembered, we have already discussed. Del equals to 1 minus summation pj1 plus summation pj2 minus summation pj3 plus summation pj4 and so on. We have combination of two non-touching loops and combination of three non-touching loops. So pj4 is not in use for us. Please put the values of minus pj1, that is the single loops. We have four single loops, p1, 1, p2, 1, p3, 1, p4, 1. pj2 is again three combinations of two non-touching loops. So we have put all these values to find the value of del. After calculating del, we'll calculate del i's. Here we need two del i's because we have two forward path P1, P2. So we'll calculate del 1 and del 2. To calculate del 1, we will see path 1, forward path 1, P1, which is G1, G2, G3, G4, which is the straight line in this signal flow graph. And because all of the loops are actually touching forward path 1, therefore del 1 equals to 1. To calculate del 2, we'll see forward path 2, that is P2, G1, G5. The gain of the second forward path is G1, G5, which is from Y1 to Y2, Y2 to Y3, and then Y3 to Y6, and then Y7. If you see carefully, then the first loop P11, which is minus G3H2, is actually not touching forward path 2. All other loops and the combination of the loops are actually touching forward path 2. So we'll write the formula as del 2 equals to 1 minus P11. That is, we have to consider only that loops which are non-touching to forward path 2. So del 2 will be 1 minus G3H2. Please keep in mind that the formula of del i's and del is same. But to calculate del i's, we have to consider only those loops which are not touching the relating forward path. Corresponding forward path. Then after calculating del i's, we will calculate value of y7 upon y1 by putting the values of the p1, p2, del 1, del 2 and del in the formula we have set in the second step. So we put the value of p1, del 1, p2, del 2 and del in the formula and we'll get this answer. Now the next part is to calculate y2 upon y1. The formula will remain same, but the y2 is actually a non-output node, whereas y1 is input node. So we have to calculate the relation between y2 and y1. For this, del will remain same, only the forward path will change, which is now from y1 to y2, and the corresponding del I will be changed. When forward path P1 change, its corresponding del 1 will be changed. So here we have to we don't have to calculate del. We just need to calculate the forward path and the corresponding del I. So here from y1 to y2 there is only one forward path, so we have marked it as P1. P1 is 1 because the branch gain from y1 to y2 is 1. So P1 is equals to 1, and then we set the formula y2 upon y1 equals to P1 del 1 upon del, and then the calculation of del is same, which we have calculated earlier in the first part. And then for del 1 we see the loops and the combination of those loops which are non-touching to forward path 1, that is y1 to y2. So you can see here easily that the first and the fourth loop, that is minus G3H2 and minus H4, these two loops are not touching the forward path Y1 to Y2. So we can consider these two loops as single loops, and the combination of these two loops are also non-touching to forward path 1. So we'll consider the non-touching loops, two non-touching loops. So the formula for del 1 will be 1 minus P11 plus P41 plus P32, and we'll put the values of these P11s, P41 and P32 and get the value of del 1. And the next step is same, we'll put the values of these P1 del 1 del in the formula and we'll get the value of Y2 upon Y1. So after putting the calculated values of P1 del 1 and del, we'll find the value of Y2 upon Y1 is equals to 1 plus G2H3, sorry, H2G3 plus H4 plus G3H2H4 upon del. Okay, now after calculating the values of P1 del 1 and del, we'll put these values in the formula and we'll get the value Y2 upon Y1 equals to 1 plus H2G3 plus H4 plus G3H2H4 upon del. Okay, now after calculating the value of Y2 upon 1, next we'll calculate the value of Y4 upon Y1. Y4 is again a non-output node. The procedure will remain same. First we'll see the forward path, which is from Y1 to Y4 this time, and then the value of del will remain same, and then we have calculate del i's. So we can see here that there is only one forward path from Y1 to Y4. So the forward path gain is P1 equals to G1 G2. Del will remain same, and the formula of del 1 will be the same formula as for del, but we have to consider only those loops which are actually non-touching to this forward path from Y1 to Y4. So we can see from the diagram that only the loop minus H4 is non-touching to this forward path. So we'll set the formula of del I as 1 minus P41. There is no combination of two non-touching loops which are non-touching to this forward path. So we'll not write any combination of two non-touching or three non-touching loops here. Simply our formula will become Y4 upon Y1 equals to P1, 1 minus, the only loop is P4, 1 upon 4. So after putting the values, we'll get Y4 upon Y1 equals to G1 G2 into 1 plus H4 divided by del. So after calculating Y7 upon Y1, Y2 upon Y1 and Y4 upon Y1, the method is quite clear to all of you, I hope. So to calculate Y6 upon Y1, this time we have to see the forward paths from Y1 to Y6, and we can see easily that there are two forward paths, so we'll count it. The remaining method is same. The number of loops we have already encountered, the total loops, and because there are two forward paths P1 P2, so we'll calculate del i's as del 1 and del 2, and we'll put these values again in the same manner and get the value of Y6 upon Y1. So I hope you will complete it in the same manner as we have done the previous examples. Up till now we have seen the Missus-Gann formula for output upon input, that is for the output node and input node, that is Y7 upon Y1, and Y2 upon Y1, that is non-output to input node, the relation to get the relationship between non-output and input node. Now we'll use this formula between output node and non-input node. So the output node is actually Y7 here, and Y2 is non-input node here. We can use this formula to find the relation between output and non-input node. But for this we have to consider this with reference to the input node. So for Y7 upon Y2, actually we'll calculate Y7 upon Y1 and Y2 upon Y1, which we have already calculated in this problem, and we'll put the value of Y7 upon Y1 and Y2 upon Y1 to get the value of Y7 upon Y2. So we'll put these values and we'll get the value of Y7 upon Y2, which is written here. You can see here. Up till now we have seen the Mason's-Gann formula for output upon input, that is for the output node and input node, that is y7 upon y1, and y2 upon y1, that is non-output to input node, the relation to get the relationship between non-output and input node. Now we'll use this formula between output node and non-input node. So the output node is actually y7 here, and y2 is non-input node here. We can use this formula to find the relation between output and non-input node. But for this we have to consider this with reference to the input node. So for y7 upon y2, actually we'll calculate y7 upon y1 and y2 upon y1, which we have already calculated in this problem, and we'll put the value of y7 upon y1 and y2 upon y1 to get the value of y7 upon y2. So we'll put these values and we'll get the value of y7 upon y2, which is written here. You can see here. So we see the multiple application of the gain formula to calculate the relationship between output and input node, to calculate the relationship between non-output and input node, and to calculate the relationship between output and non-input node. So we can apply this formula in multiple scenarios to find multiple relationships. Now this is the third example. This is the transfer function of an interacting system. We are going to find y of s upon r of s. So clearly there are four loops here. At the top right, this is L2, top left L1, bottom left L3, and bottom right L4. So we'll solve it in the same method we have done previously. Okay, the first step in applying the Mason's rule to count the number of forward paths. Here, if we see closely to the signal flow graph, we have two forward paths. The one starting from R of S, going through top two loops, passing through G1 and then G2L1, G2H2, and then G3H3 loop and G2. So the branches involved in this forward path is G1, G2, G3, G4, the upper path, and the second path is from passing through loop 3 and loop 4 from R of S to Y of S, that is G5, G6, G7, G8, the lower path. So we have two forward paths. The two forward path gains are G1, G2, G3, G4, and the second forward path gain is G5, G6, G7, G8, and the next step is to set the Mason's formula according to the number of forward paths we have just counted and calculated. So the formula here will become P1 del 1 plus P2 del 2 upon del. So now we will calculate del i's to complete y of s upon r of s. And now in the second step, we always calculate the number of single loops to calculate the value of dels. Here we have just discussed that we have four loops, L1, L2, L3, L4. The two left loops are L1 at the top left, L2 at the top right, L3 at the bottom left, and L4 at the bottom right, and the loops are L1, L2, L3, L4, and the corresponding loop gains G2H2, G3H3, G6H6, and G7H7. So here we have four loops. Now we'll calculate the gains of two non-touching loops. So here it is clear from the diagram that at the top left loop is not touching or don't have any common node with the lower two loops. So the combination of L1 and L3 is become a pair of two non-touching loop. Similarly, the combination of L1 with L4 is again making a combination. Similarly, L2 is making a pair with L3 and L2 with L4. So we have four combinations here: L1 L3, L1 L4, L2 L3, and L2 L4. And you know that the here P12 is the first combination of two non-touching loops. P22, the later one, 2 is for two non-touching loops. This is the second combination, the third combination, and the fourth combination. So we have four combinations. No combination of three non-touching loops are available here, because if we consider any three loops, there is at least one common node. So there is no combination of three non-touching loops here. Next, we'll calculate the value of delta. The formula is again the same we have used in the previous examples. Del equals to 1 minus summation pj1 plus summation pj2 minus summation pj3 plus summation pj4, and so on. Here we have a combination of two non-touching loops and we have four single loops, but we don't have any combination of three non-touching loops. So the formula will become here del equals to 1 minus sum of non-touching loops plus sum of combination of two non-touching loops, and so on. We'll put the values of these L1, L2, L3, L4. Please keep in mind that this is the summation while we calculate the loop gain L1, which will be the product of the branch gains. When we calculate the forward path gain or we calculate the loop gains, we take the product of the branch gains. Whereas when we use this formula, we use the summation sign for individual loops, either single loops or the pair of two non-touching loops. Okay, now to calculate del 1 and del 2, we see that to calculate del 1, we will see the corresponding forward path 1, which is the upper path passing through G1, G2, G3 and G4. So the two lower loops are actually non-touching to this forward path. So to calculate del 1, we'll consider the two lower loops while we are considering forward path 1. So this is 1 minus L3 plus L4. Similarly, to calculate del 2, we see the forward path 2, which is the lower path G5, G6, G7, G8 passing through this lower path. So the two upper loops are actually non-touching to this lower forward path. So for del 2, we'll consider loop 1 and loop 2. The formula will become 1 minus L1 and plus L2. So we'll put the values of L1 and L2, L3 and L4, and we'll complete the values of del 1 and del 2. Please note here that there is no combination of two non-touching loops, which is actually non-touching to any forward path. Therefore, we are not considering any pair of two non-touching loops. So we have calculated the values of forward path gains P1, P2 and del i's, that is del 1, del 2. So we'll put these values of P1, del 1, P2, del 2 and del in this formula, and we'll get the value of y upon r. So the y upon r, to calculate the value of y upon r, you have to put the values of L1, L2, L3 and L4 in this equation and you'll get the right answer. Okay, now try one more example to find the transfer function output upon input in S domain. Here we have to see carefully about the number of forward paths, about number of loops, the combinations. So we'll consider first this diagram for the number of forward paths. Okay, the first forward path is starting from the input node, passing through right node, which is marked as, the branch is marked as V1 for forward path 1. Then the next is 1 upon S square plus S is the branch gain. Then we go down because the straight line is actually not directing outward or towards the output node. So we'll go down having the branch gain 10, then we'll move right 1 upon S, again move up 1 upon S, and then up to the output node 1. So the product of all these branch gains will become the gain of forward path 1. So forward path gain 1, that is P1, is 1 multiplied by 1 upon S plus 1 multiplied by 1 upon S square plus S multiplied by 10 multiplied by 1 upon S multiplied by 1 upon S. This is the first forward path. Let's see, is there any other forward path? The second forward path is marked here in the right diagram, at the right hand side, which will start from the input node and going downward, marking as P2, which is a branch gain of 1 upon S square plus 4. Then we move right 8 upon S plus 8 is the branch gain. Then we go straight 1 upon S, and then we go up 1 upon S, and then we go up to the output node with a branch gain of 1. So the product of all these branch gains will become the gain of forward path 2, that is 1 upon S square plus 4 multiplied by 8 upon S plus 8 multiplied by 1 upon S multiplied by 1 upon S. So this is the second forward path. So again, as we have two forward paths, so we'll set up a formula, Mason's gain rule. To find the transfer function, we have marked as output upon input, y upon r. That is for two forward paths, p1 del 1 plus p2 del 2 upon del. Now we'll count the number of single loops. Here, the first single loop is at the top left, that is L1 is minus 4 upon S square plus S. At the top right is the second loop, second single loop, that's branch gain is minus S. The third one is at the bottom left, minus 7 into 8 upon S plus 8, that is minus 56 upon S plus 8. The fourth one is at the bottom right, minus 6 into 1 upon S, that is minus 6 upon S. And if we see carefully, we see that the pentagon at the right hand side is also a loop, with the product of the branch gain written as L5 or P51. This is 10 into 1 upon S into 1 upon S into 3 upon S plus 3 multiplied by S upon S plus 2. So we can see here 5 single loops, which is L1, L2, L3, L4 and L5. And now after counting the single loops, we can see easily here that we have 5 combination of 2 non-touching loops. L1 is non-touching to L2, that is these two loops are not sharing any node. L1 is also non-touching to L3, making a combination L1, L3, L1, L4 and L2, L3, and L2 and L4 are also non-touching. So we have 5 pairs of non-touching loops. Similarly, we can see in the diagram that we have 3 non-touching loops, 3 combination, L1, L2 and L3 are non-touching, and similarly L1, L2 and L4 are non-touching. L5 is actually common to L1, L2, L3 and L4, all loops, so it is not actually making any combination. Okay, now after so many examples we have calculated all summation pj1, pj2, pj3, pj4 and so on. So I hope you can calculate del easily, and I have written the formula here. You just put the values we have calculated and get the value of del. Similarly, to calculate del 1, we will see forward path 1, P1, and only L2 is non-touching to forward path P1. Therefore, the formula will become 1 minus L2. We have just put the values of L2 and then we'll get del 1. Similarly, for del 2, we'll see the forward path P2. And L1 and L2 both are actually non-touching to forward path P2, and the combination of L1 L2 is also non-touching. So del 2, the formula of del 2 will become 1 minus L1 plus L2 plus L1 L2. So we'll put the values and we'll get the values of del 1 and del 2. Calculating the values of P1, P2, del 1, del 2 and del, we'll just put the values in the formula and we'll get the answer. This is an electrical network. We have to find the transfer function V3 upon V1. This is from the very beginning, that first we have to decide the number of variables, then we have to write the equations for this network, then we have to write equations in the prescribed format we have discussed earlier, that output equals to the remaining part of the equation. So we'll have how many variables, how many output variables possible in this circuit, then we'll have that much equations. For example, if we have 4 possible outputs, then we'll have 4 equations. So first we'll decide about the number of variables, then that actually helps us to find the number of nodes, and we'll write equations, then we'll connect these equations in the signal flow graph, and then we'll apply Mason's formula to find the transfer function. Up till now we have discussed some block diagrams and some signal flow graphs. Now we'll see how first we construct a signal flow graph for a network, for an electrical network, in which we have to find the transfer function V3 upon V1. Obviously, to make the signal flow graph, first we have to decide about the number of variables. We'll have to see the cause and effect relationship, what variables are causing what effect in the network. We can see from the network diagram that we have 5 variables actually. These 5 variables are V1, I1, V2, I2 and V3. We have arranged in a straight line in cause and effect form. First, I1 is actually the effect of voltage V1. When V1 builds up, I1 starts flowing in the first loop. When I1 starts flowing in the first loop, V2 builds up, and then when V2 builds up, I2 starts flowing, and the voltage V3 built up in the next right part of the electrical network. So we have arranged it in this manner: V1 I1, V2 I2, and V3. Next, we have written here the equations for this circuit. It is quite obvious that we have decided the number of variables or the number of nodes V1 I1, V2 I2 and I3. So in this network, the 4 possible output nodes are V3, I2, V2 and I1. So it means that we'll need 4 equations. So we have made 4 equations here. I1, for the first is I1 equals to 1 upon R1 V1 minus 1 upon R1 V2. It is quite simple to write simply applying KCL and KVL to the network. Then we have an equation for V2, and then we have an equation for I2 and V3 respectively. Then by using these equations, we'll make simple signal flow graph. We can easily draw the signal flow graph. I hope you have remembered in the previous lecture we have constructed signal flow graph with the equations. So first equation, I1 is output. It has V1 and V2 two branches. So first branch I1 equals to 1 upon R1 V1. So V1 is input, I1 is output, 1 upon R1 is the transfer function or branch gain. The second is V2 is input, I1 is output with a branch gain of minus 1 upon R1. So this is how we have constructed 2 branches for the first equation, and similarly we have constructed the remaining branches. We have already discussed in detail in the first example. So this is how we construct the signal flow graph for this equation. Here in the signal flow graph, it is clear that V1 is the input node, but there is no output node here, because the definition of output node is that output node is that node which has only incoming branches. So V3 here also an outgoing branches towards I2 with a branch gain minus 1 upon R2. So in this case, we have to make a dummy node with a branch gain 1. So here we have marked a dummy node. Then the node name will remain same, that is V3, and it will connect with the V3 by a branch gain 1, and the signal flow graph will change in this manner. Here in the signal flow graph, it is quite obvious that V1 is the input node, but there is no output node, as according to the definition of the output node. Output node is that node which has only incoming branches. So V3 also have an outgoing branch with a branch gain of minus 1 upon R2 towards I2. So to make an output node, we have again marked a node V3, and we will connect it with the previous V3 by a branch gain 1, and the modified form of the signal flow graph will be like this. This is the final of the signal flow graph, final form of the signal flow graph. Here V3 is equals to V3. We have added a branch with a branch gain 1, and equation for this new branch will become V3 equals to V3, that is, it will remain same, and we have made a dummy node such that we have an output node. Now in this final signal flow graph, we'll mark loops and pair of non-touching loops, and we'll apply the Mason's rule to find V3 upon V1. We can see here that there is a single forward path along a straight line from V1 passing through I1, V2, I2, V3 towards V3 with a branch gain of R3, R4 upon R1, R2, and so we have set the formula V3 upon V1 equals to P1 del 1 upon del, and here we have 3 single loops. It is quite obvious from the diagram. The first one has a branch gain minus R3 upon R1. The second one has a branch gain minus R3 upon R2, and the third one has a branch gain minus R4 upon R2, and there is only one pair of 2 non-touching loops, that is L1 and L3. And we have taken the product of the branch gains of the 2 loops, and then we have put in the formula del, the similar formula, we have used many times in the previous lectures. That is del equals to 1 minus summation pj1 plus summation pj2 minus summation pj3. Here we have only summation pj1 and summation pj2, so we'll put the values of these, and del 1 equals to 1 because all the loops are actually touching forward path 1. After calculating all the values, we'll put the values of P1, del 1 and del in this formula, and then we'll get the final transfer function V3 upon V1. Now next is the example of mechanical network in which we have two masses and with two corresponding displacements x1 and x2. So in this example, we have to decide the number of variables and the number of, that is the number of nodes, and then we'll write the equations. First we have to draw the mechanical network, and then we'll see how we'll mark the variables as nodes, and we'll write the equations, and then we'll construct the signal flow graph, and then we'll apply the Mason's formula. Now this is the corresponding mechanical network of the previous mechanical system. So here the two masses are connected with the ground. We have discussed it in the modeling chapter, how we draw the mechanical networks. So we have constructed on the same manner. We have two displacement x1 and x2. So here we have actually for a particular system, the masses and the spring values and the friction are constant. So we can see here that we have three variables. The first input F is variable. We can change the applied force, and the two displacement x1 and x2. When we change the value of the force F, then the displacement x1 and x2 will be variable. So here we have three variables F, x1 and x2. So we have to write two equations, one for x1 and next for x2. And the order of these variables will be starting from F, then F causes a change in the displacement x1, then a change in displacement x1 will cause a change in x2. So we'll arrange in this manner F, x1 and x2. So here how we marked the variables as node to construct the signal flow graph. These are F, x1 and x2. As we have three variables F, x1 and x2, so there are two possible output nodes x1 and x2. It means that we'll need two equations, one for x1 and another one for x2. So we by observing the mechanical network, we will write the equations in the same manner we have written for the differential equations. So first equation is at node x1. We have taken a final equation for x1 from node x1 equations, and second equation we have written on node x2, and we have taken equation for x2 from the second node equation. So we have two equations, one for x1 equals to 1 upon AF minus k1 upon AX2, and another one is x2 equals to k1 upon BX1. We'll use these two equations to construct the signal flow graph. In the first equation we have two terms. It means that we'll have two branches we'll have to make two branches using equation number 1. In the first term, x1 is output, F is input, so branch will be directing from input to output, that is from F to x1 with a branch gain of 1 upon A. The second term is minus k1 upon A. Input is x2, output is x1 with a branch gain of minus k1 upon A. And second equation has single term, x2 is output, x1 is input, branch will be directed from input to output with a branch gain of k1 upon B. Again, there is no output node because x2 node has outgoing branches too. Therefore, we have made a dummy node x2 with a branch gain 1. So now we'll write Mason's formula. We'll apply Mason's formula on this signal flow graph. Now we'll apply the Mason's formula. We'll follow the same steps. First we see the forward path. There is only one forward path. P1 is equals to K1 upon AB. We set the formula X2 upon F as P1 del 1 upon del. So here we can see easily that we have a single loop. That is L1 equals to K1 square upon AB. There is no combination of two non-touching or three non-touching loops. Then we have set formula for del. We'll put the values of 1 minus L1 as we have only a single loop, and the value of del 1 is 1 because the only loop is touching the forward path 1. So we have calculated all the required values. Now we'll put the values of P1, del 1 and del we have just calculated, and we'll see that the transfer function or the output x2 upon f input will be equals to K1 upon AB minus K1 square. Sometimes it is difficult to find the transfer function with the block diagram reduction method. So it is also possible that we convert our block diagram to signal flow graph. We have to follow the following rules. We'll replace every block with a branch in the signal flow graph. We'll replace each combination of summer and pickoff points with a node, and we'll replace all pickoff points which are not connected to summer with a node labeled with the variable assigned to pickoff points. It is very simple. We'll do it, and for each input we'll show a node labeled with the variable to the input variable, and we can add any unity branches as and where we need it. This is a short summary how we'll convert block diagrams to the signal flow graph. We can simply replace a block by a branch gain having the transfer function of the block diagram, and how can we connect the parallel path and the feedback loops to the signal flow graph. This is the first example of the signal flow graph conversion from block diagram to signal flow graph. We have converted simple loops and parallel paths to the loops and parallel paths in the signal flow graph, and then we will apply the Mason's formula to find the transfer function in the signal flow graph. After constructing the signal flow graph from the block diagram, we'll apply the Mason's formula and we'll see the forward path and loops and the value of del and del i's, and then we'll find the transfer function C upon R in the same manner we have done previously. This is another example of the conversion of block diagram to signal flow graph. Again, we have changed our block diagram to signal flow graph by observing the block diagram's points, and then we'll apply the Mason's formula to this signal flow graph. This is a similar procedure we have followed previously. We have seen the forward paths and loops, and we have calculated del i's, and we find the transfer function C upon R using the signal flow graph constructed from the block diagram. This is a block diagram. We have to find the transfer function C upon R. We have converted this block diagram into the signal flow graph. I hope you can do it easily. And then we have applied the Mason's formula to the signal flow graph, and we have found the transfer function C upon R, that is T here. This is a block diagram. We have to find the transfer function C upon R. We have converted this block diagram into the signal flow graph. I hope you can do it easily. And then we have applied the Mason's formula to the signal flow graph, and we have found the transfer function C upon R, that is T here. This is how we have converted the topics of block diagram, construction and reduction, signal flow graph, construction and reduction, and the conversion of block diagram to signal flow graph. So we have completed these topics now.